Hello everyone, we are continuing the tutorials on Introduction to AVL, and today we will be continuing from the last time that we discussed the underlying principles for the software and what it does, and we will try to dive into what we are going to do and how we can use the software, where we can get it, and go through some examples. So the recap from last time, we covered the basics. What is the AVL useful for? How does it work? And what are the underlying aerodynamic principles? This time, we're going to go through the program structure. We're going to answer these questions. Where can I download it? How can I open and run it? And what files are needed? And what test files are there? What are the sample files that are available with the AVL package that we can download from the AVL website? Additionally, we will go through two sessions that are included in the files that are available with the AVL package on the AVL website. So let's get into how we can download, where can we find the software, and how we can download it. So the easiest way would be to just search for AVL Mark Drela. So if you search that, here the search engine is Bing, but you can also use Google or any other search engines that you have. If you use these search parameters or words, the first result should be what you're looking for, and if not, you can directly type in this address and go directly to that website. So we're going to click on this web page or link that will bring us to the web page for the software that is provided by Mark Drela. So as you can see, the web page is not too modern, and it doesn't have the whistles and bells of the newer, nicer websites. But for the sake of these tutorials, what we're interested in is the functionality of the software and how it can help us with the analyses that we need to do. So as you can see, it has the AVL Athena Vortex Lattice. It is an aerodynamic analysis, trim calculation, dynamic stability analysis, and aircraft configuration development. So here is a summary of the software, which we discussed last time, and we mentioned that it was taken directly from this web page. And it is mentioning again that it is using the extended vortex lattice method, which will help us with the aerodynamic calculations. So this portion is the aerodynamic analysis, all the things you can do, the trim calculations, all the things you can do, the mass properties, all the things you can do, and the eigenmode analysis, all the things you can do. We try to cover these one by one in the following tutorials, but for this time we are just looking at all the possibilities or all the functionalities that this piece of software allows us to do. It is also released under the condition or the license of GNU General Public License, which basically is a very permissive license for you to use and for you to share with others. And you can see the latest announcements and the software piece itself. So under this software, we can see multiple packages. The first one is a package that has the source codes, the sample files, and the help file for this document. The help file is also directly accessible under Documents under AVL_doc. It also includes the sessions that we're going to discuss today, which is session 1 and session 2, which are basically two samples, step-by-step instructions of how you can run them and what results you're going to obtain to help you quickly get into the functionalities and the steps you need to go through to get to those functionalities and results with this software. So the first thing we need to download is AVL 3.36. This package is the version, so 3.36 is the version. As the time goes, Mark Drela may release additional updates with higher versions, but at the point we are recording this video, this is the latest version. So this is one file that we need to download. So I'm going to just click on it and it will download it to my downloads folder. The other file you need is going to depend on the system that you're working with. So if you're working with Windows, there is the Windows executable file. So this is going to be the Windows executable file. If you're working with Mac for Apple, this is the file that you need to download. So remember that depending on which operating system you're using, you either need to download the Windows executable or the Mac executable. So I'm using Windows. I'm going to download the Windows executable file as well. Now that that is downloaded, I need to go to my downloads folder. So going to the downloads folder, we see there is the first file, that is the AVL 3.36, and I'm going to extract this into this folder. And the other file that we have is the Windows executable. So I'm going to also extract that into this folder. Now let's first go to the folder that has all the other documentation except the executable file. So let's go here, there's AVL, and we have a bunch of folders in documents. So what are the important ones? The first thing is the AVL_doc, which is the documentation or the help file for the AVL. If we open this document, you can see that this document is just a notepad or the .txt document. It's a text file. So it is not a very modern help file, but it does have a lot of information. So the easiest way to get around this is to use the menu, find, and just search for whatever information you need. If you're stuck in a section, the definition of a section or anything like that, you can just search for it in this file and you should be able to find it. Now, it is very extensive and it is a very long document, and it has a lot of information on all the things you need to do with this document and with this software. We will try to cover some of them as we go through the tutorials for the introduction to AVL, but we may not be able to cover everything. So it's important that you use the find function in the notepad to find whatever you need. If we haven't covered it and you come across the need to use that piece of information or the need to use that particular functionality in the software. So this is the AVL doc txt, and that is the help file basically. Then we have two sessions, session 1 and session 2. We will get to these sessions later on. And then we have a bunch of folders. So these folders include the source file for the AVL, which is written in Fortran, a programming language that was very famous and popular back in the day, but is not as much used these days. You also have some other folders for the required libraries and other things that are needed to run the software. And then we have the runs folder. The runs folder has a lot of sample files for various designs, and we will try to go through them as we're going through the session, session 1 and session 2, which will be using some of these sample files. Now, what are these sample files? You will see basically 4 different extensions or file formats in this folder. The first one is .dat. .dat is basically a data file. Usually these ones include information about an airfoil and the characteristic of a certain airfoil. You can import these for unknown airfoils to the software, or you can actually use predefined NACA airfoils in the software to use their characteristics. Next, we have .avl. The .avl is the geometry file. The geometry file is used when you want to define, design, and work with the geometry or the overall shape and configuration of your flying object or airplane. Next, you have the mass file. The mass file includes the information about the mass distribution for your design or aircraft, and it basically will help identify the center of gravity, the inertia, and other things that are required, particularly for the dynamic analysis when you're running the eigenmodes and the stability analysis for your design or aircraft. The other file you have is the run file. The run file includes information for various scenarios that you want to run and test your design against. For example, if you're going to run a same simulation, but you want to change particular things in various iterations of that simulation. For example, you want to change the angle of attack from, for example, 0 to 10 or 0 to 20, and you want to see the result for any of those iterations from 0 to 20 degrees. The run files will help you store that information in a set and then run through them in a batch without having to run them individually, and then allows you to either see all the information or results or store them in a file and then retrieve them later for your reporting or additional analysis. There's also another file format here that is the EIG, which basically stands for the eigenvalues or eigenmodes, and this is particularly useful when you're analyzing the stability of your design or aircraft, and we will get to those as well when we get to definitions and functionalities of the software and we try to dive into them individually. So that basically covers all types of files that you need as input and output from this software. And this is in the full package, then the AVL folder and the runs folder. Now, these are basically the main things that we need to discuss. The rest of these are just for the source code and for additional source access and libraries if you were to further develop this or modify this, which is not the focus of these tutorials. The next thing and the main thing that we actually need to get into is the actual executable file. So if we go to the AVL 3.36.exe or executable file, we see that there is one file that is with the extension .exe. Remember that this is for Windows operating system. If you're using the Mac version, you will see a different file type, but you should be able to run that in a Mac. Here we're working with Windows, so we're going to use this executable file with the extension .exe. So to open this, I just need to double click, and this will open the main window for this software. Now, the main window for this software is not by default of this size. What have I done? It's usually smaller in size, but to be able to better see all the text, you can right-click on the title bar, click on Properties, and then here you can change the font name and the font size. So by default, I think it is around 10 or 12, but I've made it bigger, 28, so that it is more readable or legible. You can also change some of the other options for the layout, colors, and other things to your liking if you were to use this terminal for working with the software. But right now it's good, and we are here, we are in the main screen of the software. As you can see, it has some disclaimers and information about who wrote this, the version, and we also have the main menu. So if we type quit, it will exit the program. And then we have the modes. We have the operation mode for computing operating point run cases. We have the dot mode, which is the eigenvalue analysis of run cases, which is basically for stability analysis. We have the dot time, which is the time domain calculations. And then we have the menu to load the files. So load F is the file name, will read the configuration input file. So this load will need a .avl file. Mass will load a mass distribution file and will need a .mass file. And case will run or will open a run case, which is basically the .run file. So these are the three main file types that we can load individually, as we discussed, from the files that we have. And we saw some examples provided to us from the main package or the big package that we downloaded from the website. We also have some additional options here. So the cint will clear and initialize run cases, and the mset will apply mass file data to stored run cases. So these are basically if you were to use these for mass or batch calculations. Finally, we have the .plot, which will change the plotting options. So you have some room to change the plotting options. This software is going to plot some diagrams to help you better visualize and understand some of the concepts and the analysis that you're working with. And finally, we have the name that will specify a new configuration, which basically is if you were to load or save additional files or configurations. So this is all the menus or the options we have in the main menu. Now, as you see here, we have the AVL, the main command line, and we have a blinking cursor, which means this program is now ready and is waiting for us to input any of these commands so that it can run them and give us some results. Now that we are in this, let's go and let's get started with the sessions, the session 1 and session 2 that we already downloaded, and let's go through them step by step. So what I'm going to do, I'm going to go back to the download folder, and I am going to try to find session 1 and session 2. So we go here, and we find session 1 and session 2. So let's just first open session 1 and then session 2. So we're going to keep session 1 open. And something else we need to do is I'm going to close this code here, and I'm going to go to the executable file, and I'm going to copy that file to the run folder. Why do I do this? So I'm going to copy this, or right click and say copy. And then I'm going to go to the AVL, to the run folder, and here I'm going to paste it. The reason I'm doing this is because when you open AVL, by default, it will read and write files to the directory that the executable file is in. If the files you're working with, like the configuration, the mass, and the run files, are not in the same folder as the executable file, for each time that you're going to open files or load any configuration, run, or mass file, you have to type in the full path to that file. But if the executable file and the files that you're going to load are going to all be in the same folder, you just have to put in the name of the file instead of the full path of the file. So basically it will make life easier. So in this case, I'm going to open the AVL again. As you can see, I changed the location of it, so it went back to the default size that it had. So I'm going to make this a little bit bigger. And I'm going to try to put that there, and then I'm going to put session 1 on this side. So we have a side-by-side view of session 1 and the program. So what we can do is then we can go ahead and try to type in these commands one by one and see the results. So session 1 says the typical AVL session keyboard inputs. All commands can be in lowercase. Blank lines below are for clarity, they are not returns. Indentation in the command listing below indicates the menu level to help navigation. And a command in quotes, for example L, means that the letter is typed when the cursor is in the plot window rather than the text window. So we go through these. Now we have start AVL with an input file argument such as the plain vanilla case. So we have cd runs, and then we have bin AVL vanilla. Giving the .avl extension is optional. So what this says is we are in the main menu and we already copied the executable file in the runs file. So we don't have to change the directory to the runs file or runs folder. What we need to do is we need to load the vanilla files. So what we have to do is going to be vanilla. If we type in vanilla, we see that it is not doing anything because this command is asking us to run AVL vanilla. It still doesn't recognize. So what is happening? These commands are if we were to run these from a command prompt, not from the actual AVL. So that includes the AVL in the command line. But now that we are in the AVL executable file, all we have to do is to load the vanilla. So what we are going to do is we want to load a configuration file. So we're going to say load and we want to load the vanilla. So we load vanilla. We can optionally add AVL to it, or if we don't, it will by default add the AVL to the file name. So you see now we were successful. We were able to load the geometry file, which is for the vanilla airplane. The configuration name is plain vanilla or vanilla airplane, and it gives us a bunch of information about that configuration. So it gives us that it has a wing, it has a G-stab, and it has a V-stab. So H stabilizer or horizontal stabilizer, and V-stab, vertical stabilizer, and the wing. So these are the three main surfaces that this configuration has. It also gives us a list of the bodies, surfaces, strips, and vortices, and control variables that are loaded in this configuration. Now, the next thing we have is saying to go into the oper menu or operation menu. So we're going to type in oper in here. You see that we have entered the operation menu. So operation of run case 1 out of 1, it doesn't have any names. It gives us some variables and some constraints, which in this case, all of them are set to 0. And we have some additional option menu, which we will try to cover some as we're going through this session. So the first one is going to be, again, following the steps in here, G. if you see G here, it stands for geometry plot. So if we type in G, it's going to plot the geometry and enter the geometry plot. So let's type in G, enter. What it opens for us is the geometry window or plot. Now with this one open, we see that there are new options appearing here. So we have some options that we can use to change the view of this. What do we do with it? So if we say K, enter, it will enter the keystroke menu. So we're going here, we find K, it says K stands for keystroke mode, K, type. Now it says L, move the viewpoint to left. So I am on this menu, I'm going to press L on the keyboard. As you see, it is rotating my view for the configuration or design for this aircraft. You can do it one by one, or you can just hold the L key and it will rotate. R will be turning right, so it will basically rotate the configuration in the opposite direction or right direction. D will turn it downward to the maximum of 90 degrees, and U will rotate it upward to the maximum of 90 degrees. You also have the option to ingress with I, and you have the option to outgress with O. So ingress, outgress. So this is basically to change the perspective of the view that you have. Now we're going to press space to exit the keystroke menu. Now we're back again in the main menu. Now here we have TR. If we type this, we will get the trailing wake vortices. So we're going to go here. We find TR, it says TR is the trailing legs, and we press enter. Going back to the menu, we can see the trailing wake vortices. And we can again change the perspective to see them differently from a different angle. If we type TR again, it will going to hide it. And if we press return or just press enter, we go back to the operation menu. So I press enter and you see we are back in the operation menu as shown here. Now we want to change some of these variables and constraints. So here we're going to type AA1 to set the angle of attack to 1 degree. If you see here, A for alpha or angle of attack is now set to 0. To change this, I'm going to press A, and 1 as is shown here in the instructions in session 1, and I'm going to press enter. Now you see that that value is changed from 0 to 1 in the current configuration for our run case for this design. Next, if we press X, if you see here, is execute run case. So if I press X and then press enter, it will run or execute the run case for us and gives us all these numerical details for all the information we have for this particular design. So we will have the reference values for the wing or surface areas, the chord, the span, and XYZ values. And also we will get all the other information that we will try to get to, but a lot of these variables are actually the derivatives that are used for the analyses that you use when you're analyzing a particular design for your geometry or aircraft design. So this is a very simple case with very simple restrictions or configurations, but it is just to show you how to set or change these values and execute, basically run the simulation and get the result. The other thing we can get from this is a TREFS plane, which basically gives us the lift distribution and other information for the wing. So for this, if you see here, letter T will give us the TREFS plane. So I'm going to press T and I'm going to press enter. Now if we go to the plot, this is a TREFS plane. So the TREFS plane is going to give us the lift distribution. So you can see we have the CLL, CL, and then CLC over CREF and alpha. So these are basically some of the main values or the trends you're looking for when you're looking at the lift distribution or lift coefficient distribution and all the angles of attack at different sections of your wing. It will additionally give you some information about the design or the wing that you're working with. That includes the lift coefficient, the moment coefficients, the drag coefficients, the induced drag coefficients, and the Oswald efficiency factor. If you remember this E value, we discussed last time that for an ideal optimal case, this value is going to be equal to 1, which is for an elliptical wing. We know from the geometry that we looked at from this plane that this wing design is not an elliptical wing design. So we know that this is not going to be 1, but this calculation shows us or gives us the value of this as well. If you have any control surfaces that are active, it will also give you the values for the control surfaces. And we here see the angle of attack alpha, the bank angle beta, and the moment m. So this actually gives us a lot of information about the run case and for the geometry that we have, given the restrictions or the constraint we have set for the analysis or for the run case. Now we go back again to follow additional commands from this session. So here we see that we have to go back, press enter to go back to upper menu. So again, we're in the upper menu. So we're here now. And now we're going to change another constraint. So we have AC to 0.6. This is to set the alpha or the angle of attack that gives us the lift coefficient of 0.6. If we go to our TREFS plane, which is gone now, we would see that the CL right now is not at 0.6. So we want to find the angle of attack that gives us that value. So we type AC 0.6. And then look what are the things that are going to change here. So if I press enter, we see that we are having an alpha that gives us the CL for 0.6. Last time our constraint would give me an alpha that gives an angle of attack or alpha as 1. So we have different constraints. Now again, we type X to execute this simulation. Again, we get a bunch of values here. These values are also shown in the TREFS plane when we plot that. And additionally, we want to enter the horizontal flight trim setup menu. So we have here C1, set level or bank horizontal flight constraint. We're going to type C1, enter. So we're entering the horizontal flight trim setup menu. We have various options we can choose from. So we're going to type G. G is for gravity acceleration to be 9.8. So now G is set to 9.8. Then we need the air density, so we're going to type D 1.2. That is the air density now changed to 1.2. Then we need to set the mass as 100. So now we see the mass is set to 100. And finally, we need to set the bank angle to 30 degrees. So we set B 30. Bank now is set to 30 degrees. So after that, we're going to press return to exit this menu, and then we're going to execute this simulation or run case again, and we're going to type T to see the TREFS plane. So now we have a TREFS plane and we want to look at it. This is where our TREFS plane is. And we see that the values have changed now. To get the CL of 0.6, we see that the alpha that we need is 1.8 degrees. And with this, we see that our CL is set to 0.6. This is what we wanted. And other values have changed accordingly. The other thing we can see is we do not have a symmetric CL anymore. The reason is that we have set the airplane to bank, so it is basically rolling. When the airplane is rolling, we won't have a lift distribution that is symmetric on the wings. And this TREFS plane is capturing that and showing us what is the actual lift distribution. So now we're going to go back to the upper menu and we try to change some other variables. So we type in D2RN0, which should drive the aileron to get 0 rolling moment. Note that in the previous simulation we didn't have the moments 0, so this is note the non-zero moments. If we look at this TREFS plane, we see that the moments, the CL, CM, and CN are not 0. We want to get these to 0. That is what we're going to set now. So we have D2RM0. So we have D2 aileron is going to be set to a value that set the roll moment to 0. Next we have D3 PN0. So the elevator is going to be a value that makes the pitch moment 0. And finally, BYN0. So we will have a beta or bank angle that gives us the CN or yaw moment equal to 0. So now we have these constraints set up. We run this run case again with execute, and then we look at the TREFS plane. Now if we go to the TREFS plane, now we see that all the moments are set to 0. We have a bank angle and the angle of attack. Now we go space or enter again to go to operation menu. Finally we set D4 YN to 0. We set the rudder to get the 0 yawing moment. So we have D4 rudder for CN to yaw moment to be 0. And we set BB0 to set the side slip in lieu of yaw moment constraint to execute. Run again, X and T to get the new TREFS plane. So now you see we do have another roll. So we see that we do not have a symmetric distribution of lift. We do have all the moments 0, we have angle of attack, and we have deflecting controls. So because of the deflecting controls, this is what we are seeing for the distribution of lift. Now, let's say we want to save this plot. Here we see that H is for hard copy of the current plot. So if I press H, it will save a hard copy to a file that is in the same menu as the executable file, and it's called plot.ps. It is a PostScript file, and we need to convert it before we can use it, and we will go through that later on how to work with these plot files to get the highest quality out of them. And now we press enter to go back. We press G to get the geometry, and we want to see the surface loading distribution, which is with LO. Loading. We see the loading on the surfaces. We go to O, options menu. We set surface loading scale factor to 0.3, L 0.3. So we see here there is some changes in the visuals, just to see them better. We press enter to plot menu, enter to upper menu, and we're at upper menu. And we calculate and display stability derivatives. So if we play ST for stability derivatives, this is what we get. Now, we can either type a file name to save them or just press enter to see them on the screen. So I'm going to press enter to see them on screen. And we see all the stability derivatives are printed on this screen. And as we learn more about these stability derivatives, we can find out what they mean, how to use them, and what are the things in our geometry and design that can affect these stability derivatives to help us get to a design that works for us and meets our requirement. So that's the last part. If we press enter, enter, we're in the AVL main menu, and here we can type quit, and this will close the software and all the plots. And that is all we need for this session.